All right, in this segment, we're going to talk about types of variation in the genome. So it's variation in the human genome. So funny enough, I have to start a discussion of variation by stressing how similar humans are to one another. If you look at multiple genomes, you will see that about greater than 99% of the DNA bases are shared in any two human genomes. Shared in any genomes. Any human genomes. So that's remarkable because it means the entire diversity of humanity is due to about 1% of variation that we see in the genome. But that 1% of 3 billion is a pretty big number, and so there's lots of opportunity for lots of humans. And so humanity is sampling this variation space, and that's why we're all different. Okay. So a couple of terminology things that I want to talk about first is the idea of mutation and polymorphism, which I'll get to in a second. So a mutation we think about as a very rare and new change in DNA. So these are the connotations of mutation, are that it's rare and it's new and it's a change in the DNA. Recent DNA genome sequencing has showed us that when you have a new human, a baby, that baby will have something like 20 to 100 positions in its genome that have novel changes that were not present in the mom or the dad. So these are, you can think of these as like mistakes that were made in copying the mom and dad's DNA. So these are 20 to 100. We call them de novo mutations or changes in the DNA from the parents. So de novo changes in the parental DNA. So that's worth considering for a moment. So the first thing to consider is we're copying 3 billion bases from mom, 3 billion bases from dad. We're getting almost all of it right except for 20 to 100 of those bases. 0.00001%. So it's an amazingly good capability for copying DNA, but it's not perfect and there are these changes. And we call these changes, de novo changes in parental DNA would be a mutation. And this happens because of mistakes in the replication of the DNA. You have to make a copy. It's called replication. Mistakes in replication of DNA. Now, you can make that rate of changes go up. And the most famous way to do it is by exposure to radiation. So we all know from experience with people who've been exposed to radiation, either through, well, atomic bombs or through working at hazardous nuclear waste sites or whatever, that this rate can go up based on environmental exposures. And of course, that can be the source for many more de novo changes. And the reason we get diseases then is because these changes start to hit genes that are important for cancer or for other diseases, and it leads to trouble. So that's, when we talk about mutations, we're thinking about relatively rare and relatively new changes. The other word that you will hear is polymorphism. Polymorphisms are differences in DNA, differences in the genome that in general are not new and not rare. And I will give some examples in a few seconds of polymorphisms. But the idea is that we see them in a fair number of humans, not just the one who just got it. And we expect that these have been around in humanity for tens of thousands, if not hundreds of thousands of years. So that's a little bit of a vague definition, but I'm going to leave it like that for now, and I think you'll understand it better when we go through some examples. Now, I also need to do a couple of other definitions before we get into the good stuff. So when we're talking about the genome, an important idea is a locus. Like location, locus. A locus is a defined region of the genome. That region could be a single base, a single DNA base, such as chromosome 7, base number 23,247,140. I want to be very explicit to show that I really mean a single letter in those 3 billion. That's a loci. But it also could be an exon or an intron, which would be a bigger segment. It would be like base, 247,140 to 247,289. That would be 149 bases. So this is one base. This would be 149 bases. It might be a gene. So you could just say my favorite gene, ABCB1. That could be my locus. It could be an entire chromosome. Or it could be an intergenic region. These are really all examples. This is not exhaustive. The point is, for every locus in the genome, you will have 2 alleles. An allele, funny word, allele, is the possible sequences observed at a locus. Possible DNA sequences observed at a locus. So let's be very clear that for every locus in our genome, we will have 2 alleles, one from mom, one from dad. That doesn't mean there are only 2 alleles possible. It just means that we only got one from mom, one from dad. So let me expand on that a little bit in red. So for a single base, at this position, we may notice that some people have an A and other people have a G. In that case, there are only 2 choices, and so there are 2 alleles at that locus. There are a few loci in the human genome where there's actually 3 choices for a single base, A, G, and T, for example. So when we sequence your genome, we might see that mom gave you an A or a G or a T, and that dad gave you an A, a G, or a T. So there are 3 alleles at this loci, would be the way we would say it. For exon, it's 149 bases. So it's going to be some sequence from mom, some sequence from dad, but there may be other sequences that are present in other people, and so there could be more than 2 alleles easily. And in fact, for genes, there could also be multiple alleles, chromosomes, intergenic regions. So important that we have locus defines where we're looking, allele defines the choices at that location. Okay, I think that's enough definitions. Now we can actually talk about the types of variations that we observe in the human genome.